My name is Jeff Gehlbach, and since 2007, I've worked in many different roles at the OpenNMS group. I'm now a technical product manager with an additional charter for evangelism about our growing portfolio and the importance of doing things in the open source way, as we've always done them around here. I'm sad not to be there in person with all of you this afternoon, but I will be taking questions live at the end via Jitsi Meet. Thanks to the NETWAYS team, particularly Bernd and Marcus, for having me and for their flexibility in this regard. My purpose here today is to explore a case study from a real customer environment that we dealt with here at OpenNMS. When we started down this road, OpenNMS totally lacked flow support. The customer in question was a major sponsor of the development work required to get us to the point of handling over 250,000 flows per second. As with everything we do in the OpenNMS project, all the work was done in the open and is entirely free and open source under the Affero GPL v3. I'd like to give credit right up front to my colleagues Jesse White and Stefan Wachter, who presented an internal tech talk from which I've borrowed liberally for this presentation. Let's get into it. I'll open with a brief refresher on flows and their key concepts, then present a high-level overview of the solution architecture and the customer's environment. Next, I'll get into some new work we're about to debut in the product around flows and streaming analytics. And finally, I'll talk a bit about what lies ahead in this realm. We'll wrap up with a live Q&A, assuming the gremlins stay away. A flow at base is just a summary of some network traffic which gets sent by a flow exporter. That flow exporter is typically on a router or a switch, one that's equipped to inspect the packets that it forwards, looking at the source and destination IP address, the source and destination port, the layer 3 protocol, and some other attributes to arrive at a tuple that identifies an exchange of data between two nodes. As these flow tuples build up, the flow-enabled device fills its flow cache with the summarized data, including the packet count and data size for that flow. Whenever some trigger occurs, perhaps a time window in time during which no new data is seen being exchanged on a given flow, the flow-enabled device sends a flow packet with all that summary information to a collector. The collector is some piece of software capable of receiving and processing flow packets. That could be OpenNMS or CFlowD or any of a myriad other free and proprietary options that exist in the market. Flow-enabled devices tend to be higher-end ones. Your average consumer device tends not to have this feature unless you're running a custom firmware like pfSense or OpenSense. So again, in a nutshell, the flow-enabled device constantly inspects traffic, summarizes it into flow records, and then sends those records in the form of flow packets to a flow collector. Now, many different flow protocols exist. Netflow V was the sort of original one. It's proprietary to Cisco and first appeared in 2002. It's not very extensible, and it supports only UDP as a transport mechanism, but it does solve some of the basic problems of network visibility, and it's still useful today. A couple years later, in 2004, Cisco shipped the improved version of Netflow, which is called Netflow V9. It's still proprietary, but it is significantly more extensible than Netflow V. Now we have the successor to Netflow 9, which came in 2013 in the form of IPFix. It's a standards-based protocol, very similar to Netflow 9 overall, but it is a bit more extensible, has some more security features, and supports some additional transports. And again, it's an open standard now. Here's what's actually inside a Netflow V export packet. We can see that it's a V5 packet, and here are all the various fields as dissected by Wireshark in this screenshot. I'm just going to gloss over most of this stuff, and we'll talk about only the most important fields. The first two are the conversation partners, the two hosts that are talking on the network. Their source and destination addresses, along with the source and destination ports. we get a measure of the data volume exchanged from the octets field. And from the duration field, we can know how long the exchange went on. At the very bottom here, we see this padding field, which was in Netflow 5 marked as reserved for future use. Some devices use these extra bytes as a place to indicate directionality of the flow, to differentiate between ingress flows and egress flows. But again, that's not a part of the standard in Netflow 5. It is actually baked into the successor protocols, though. Now, as we saw, Netflow 5 is pretty simple. It's straightforward. But here comes Netflow 9, and it has a lot more moving parts. You can see in this slide versus the previous one, this is a significantly more complicated protocol. It introduces such things as templates and flow sets, as well as option templates. And these things all make the protocol a lot more efficient over the wire. It's far less chatty because instead of resending the same data, it can use a template basically to say, yeah, repeat that last. But the savings comes at a cost in protocol complexity and implementation complexity. We've had to fix quite a lot of bugs in our handling of templates in particular. We think we've got them all, but you know how that goes. The takeaway from this slide really is that Netflow 9 introduces some significant improvements, but we won't get much deeper than that. Now that we've talked about a couple of flow protocols, let's get into how those protocols compare to other options, including Snmp and sflow that you're probably familiar with. Everybody knows about Snmp, at least at this conference, I imagine. But Snmp strictly gives us interface counter data, right? You get to know the total amount of traffic that's gone through an interface during a particular period of time, but it doesn't give you any visibility whatsoever into the characteristics of that traffic. That's a problem that Netflow, sflow, and IPFix can help address. We already touched on Netflow, but there is also sflow, which takes a different approach. Instead of summarizing the traffic and maintaining counters in a cache the way Netflow does, sflow samples packets. It might, for instance, inspect one packet out of every 1,000, and then it summarizes the header info from that one packet out of 1,000 and sends on that summary immediately to the collector without waiting to see when the flow ends. The collector then can interpolate what the actual usage is. So you can get the same general type of visibility, but it's important when you deal with sflow to keep in mind that the mechanics are quite different to the ones in Netflow and IPFix. sflow also has a whole bunch of other facilities for streaming other kinds of system level and interface level telemetry data. And it's kind of its own particular beast. I think incidentally that sflow originated just a few kilometers south and east of where you're all sat now at a little place called CERN. One last thing that bears mentioning here is that Netflow and sflow and IPFix are not at all the same thing as OpenFlow, which you're probably hearing others talk about this week in talks about software-defined networking. OpenFlow is a totally separate thing. It's a switching protocol which SDN switches use to talk to their controllers. Just take care about that and watch for confusion. Moving on now from that refresher on flows, let's talk about what OpenNMS actually provides in the realm of flows. We've added support over the past few major releases, I think starting in Horizon 24, for collecting, persisting, and visualizing flow data. We support quite a few flow protocols, including Netflow 5, Netflow 9, IPFix, sflow, and some Juniper-specific protocols that we also have baked in support for at the request of some of our users. Interestingly, we're, I think, pretty unique in the marketplace right now in that we can support all of these different flow protocols with a single UDP port listener. So instead of having one port for Netflow 5, another for IPFix, and yet another for sflow, you can just tell all of those flow exporters, hey, send it to port 9999 on my OpenNMS node. And we have a multilingual listener that figures out what is being spoken to it and just does the right thing. Once we get that data, we're able to enrich the flow data with inventory data about the nodes that are under monitoring in OpenNMS, so that you can see the flows actually associated with the nodes that took part in the flows, not just the router or switch that exported the flows, but actually the conversation partners. So if you're looking at a conversation between a Windows machine and a Linux server, and both of those nodes are under management and in your OpenNMS inventory, you can actually see them resolved as the endpoints that were also the conversation partners for that flow. In addition to that, OpenNMS also has a flow classification engine. You can write rules to identify flows based on their various attributes and sort them into application buckets. We ship a ton of canned rules, I think based on essentially the etc services file, and you can easily create your own using a syntax like the one highlighted here in blue, so that, for instance, when you visualize traffic like this in the dashboards, you can see the flows labeled as Quake 3 instead of UDP 666. Incidentally, there's both a GUI builder for these flow classification rules and also a REST API, which is actually what that GUI builder is talking to behind the curtain. Now, we provide pretty impressive horizontal scale for flow data. Having been battle tested in some very large environments with flow rates even higher than the one I provided in the title and abstract of this talk. I think I put in 250K, and we've actually seen 300,000 flows per second successfully handled by this solution. In the interest of full disclosure, it's not simple to achieve this level of scale. That's true of any solution, I think. As you'll see in a moment, that holds with OpenNMS too. But with proper sizing and tuning, it's possible in a repeatable way. And it's being used at these scales at real sites in the real world at some of the largest companies in the world. It helps to have a data team who can do the care and feeding of the more unruly stack components, of course. OpenNMS also provides enterprise reporting, which means we're able to push reports out in PDF format via email on a schedule. This capability is something we built specifically for the Flows project. The same customer who sponsored the Flows project also wanted this enterprise reporting feature, but it's also usable for non-flow reports, and it's really cool. You can even use it to push PDFs out via email of Grafana dashboards that don't even include any data from OpenNMS in them. Finally, a big thing we bring to the table is visibility in the form of top K or top N statistics, broken down by interface, application, host, and conversation, with filtering according to quality of service. So you can ask questions like, what are the top 5 applications that are currently using bandwidth on this particular link that's saturated at the moment? Or, I mean, let's get real. The real question is, who's torrenting the Foundation series and making it slow in the office? So here's what our flow visualization tool actually looks like. As you probably guessed, we're using Grafana as the framework for this visualization. With the help of a data source plugin that we maintain, we call it OpenNMS Helm. There's no confusion possible there, right? But that's the name that we chose for it a few years ago, and for the moment, we're sticking with it. That data source plugin talks to the OpenNMS core via a REST API to get the flow data. You'll see this in the architecture slide that's coming up. You get controls in this dashboard to choose among multiple data sources in case you have multiple instances of OpenNMS, and also variable pickers to choose the node and interface from which the flow packets were exported originally. And you can pick a differentiated services code point value if you want to get that fancy. That's the DSCP picker there. This panel is just showing us the throughput by application, but the Flow Deep Dive dashboard, which this panel is a part of, actually also has time-locked panels breaking down the throughput by application, and if it's available, which it usually is, the Snmp interface statistics for the same node and interface. This means that you can browse through the traffic volumes in the Snmp stats, look for big humps or spikes in it, and when you see them, you can drill down into the flow data over the same time period. This lets you isolate the applications and conversations that are responsible for all of that volume. Because the flow data is not bucketized in the same way that Snmp data is, you can go extremely deep into even sub-second resolution in most cases. That makes this an extremely powerful tool for getting to the bottom of what's eating up all of your bandwidth. Here's the solution architecture at a high level. On the left is the router or switch that's exporting the flows via whichever protocols you're using to a minion host. Now, minion, in brief, is an OpenNMS product. It's just like the rest of OpenNMS, open source under the Affero GPL v3, whose job is to provide edge visibility for all of OpenNMS's functionality, including flow ingest. It can also do polling, data collection, and receive Snmp traps, syslog messages, and other kinds of streaming telemetry besides flows. You can run a whole fleet of minions, and most of our biggest customers do. You can distribute them throughout your network, deploy them in pairs to get high availability and fault tolerance, put them behind a load balancer for extra fault tolerance. And you can run these either on your own or with the help of a Minion Appliance cloud offering, which we're intending to launch this month. Minion receives the flow packets, figures out which protocol they're coming in as, right? Sorts them according to whichever flow protocol they came in by, does some parsing and enrichment, and forwards the resulting document to typically a Kafka cluster, although it could be ActiveMQ. But if you've had operational experience with ActiveMQ, you probably ran away screaming and chose Kafka instead. The enrichment currently done by Minion takes the form of just reverse DNS lookups of the hosts that are mentioned in the flow packets as the conversation partners. We do this at the Minion at the edge because depending where we are in the network, right, and what our resolver is set to, our DNS resolver, the results of that reverse DNS lookup may differ at the edge versus what they would look like in the core. So we made the decision to do it out at the edge on the Minion. Also connected to Kafka is one or more Sentinel hosts. Sentinel is another OpenNMS product. It's a workload scaling node, and just like Minion and the core of OpenNMS, it's also a Affero GPL v3. It's actually just an Apache carafe that has a little bit of OpenNMS poured into it already, and you get to choose which of several different functions you'd like that Sentinel to take care of. And that gives you workload scaling capability to offload heavy work that would otherwise be shouldered by the core of OpenNMS. In this case, Sentinel is doing further enrichment, including application classification. That's those rules, right? The port 666 and these networks equals Quake 3. It's also doing inventory matching. So that's the bit that I mentioned where we were able to match the conversation partners in a flow record to nodes that are under monitoring in OpenNMS. And we also do interface tagging. That's why we've got this dotted line to the relational database, the Postgres database. The interface and node tagging is the super handy feature that we have that once we see some flow data associated with a node or an interface, we mark that interface and that node as having flow data availability. So it's a quick little shortcut way for when we present views of those nodes and interfaces in our own web app to show you, hey, there's flows available on this node, and there's ingress flows or egress flows or bidirectional flows. And you can get down to the specific interface level with that too. Once it's done with all of this tagging and inventory matching and classification, Sentinel forwards that further enriched document back to Kafka. The next component that has a turn is one that we're provisionally calling Nephron. I'll get into its job later, and the name is probably going to change, but you should know that currently it runs inside an Apache Flink cluster. Its job is to do a whole bunch of streaming analytics, and then it's persisting the results into an Elasticsearch cluster. This is where the flow record documents come to rest, at least in the current architecture. When it comes time to display that flow data, we use Grafana with a data source plugin that talks to the OpenNMS core. And the core is going to look at the Postgres relational database and at the flow record documents in the Elasticsearch cluster to pull together that inventory data and the flow record data and present it all to you. Now, if you're paying attention, you probably noticed that we also have an Open Metrics TSDB down here at the bottom right, labeled Cortex, and that's Prometheus Cortex. It's what you think it is. We haven't also used that name. It is something we're about to debut this month in Horizon 29, support for storing flow records provisionally in Prometheus Cortex. This component currently acts as a complement to Elasticsearch rather than replacing it, and I'll get into why that is in a few slides from now. So let's look at a little bit at this customer environment, what the shape of it is, what the volumes of data are that we're dealing with, and then we'll talk a little bit about some of the challenges that we've bumped up against in the course of working on this environment. Here's what the flow data looks like at scale in this real-world customer environment. These are snapshots that were taken at the end of 2019, right around Christmas time. We had 800 different routers at the time in this company's IT estate exporting flows across their enterprise. Most of them with flow processing enabled only on the internet-facing interface. A few nodes did have multiple interfaces enabled, 2 or 4 interfaces or so, and that bumped the totals a little bit higher. But in the end, this results in an average of about 6 million flows per interface per hour. That's a lot. Here's a list of the various indices in this screenshot from Elasticsearch. This is just looking at it in Kibana that hold these flow record documents. As you can see, these indices are bucketized by day and hour. So they're named like netflow-year-month-day-hour. So 00 through 0023, 00 through 23 rather. So the flows are actually bucketized by the day and the hour so that all flows for each hour go into an index together. You can actually configure this, but at the scales we're operating here, you wouldn't want to go any bigger than an hour. Daily buckets would be just untenable, I think. You'd have sharding problems. So as you can see, we have usually about 140 million documents, which are just JSON documents, right? This is Elasticsearch, filling about 80 gig for each hour. You can imagine how this adds up over the course of 3 months or 6 months or a year. It's really voluminous. And actually, the volume of flow records has grown significantly since this snapshot. And that has brought us into contact with some new and exciting challenges. Yeah, so at the moment, we're dealing with just-in-time flow statistics. We don't aggregate these flow records. We store them basically in their raw form, right? We enrich them into a JSON document that has more information in it actually than the original flow packet had. Including those reverse name lookups, those associations with the nodes that are under monitoring in OpenNMS. We're doing some DSCP and QoS enrichment. We can do autonomous system number lookups. There are all kinds of data points that can go into these records. But with such a large volume of flow record documents, we've really run into performance challenges when rendering the dashboards. The performance was actually fine when the time range covered only 5, 10, 15 minutes or so. But once you start to get into larger time ranges, such as the last day or the last week, which is actually super helpful, of course, for getting a handle on high-level trends, there's just so much compute going on that the queries become prone to timing out. Some of the just-in-time queries can take upwards of 30 minutes to run, which of course is just unacceptable for interactive use. That's ridiculous, right? You don't want to have to change a variable picker and then go get 2 coffees and come back and maybe it's ready for you to look at the result. Also, sometimes these things just time out, right? Grafana won't wait forever. So the customer set a requirement when we started to see these performance issues that any of our flow dashboards needed to be able to render inside 10 seconds. That was sort of the snappiness threshold that we established with their users for a time range covering up to 24 hours. And longer term reports covering a span of up to 30 days needed to be able to render within a 10-minute time frame. And that reporting case is actually, that 30-day reporting case refers to a batch job that runs on a schedule and gets emailed out as a PDF with that enterprise reporting framework that I referred to previously. So that longer render time is not such a big concern, but we still wanted to see if we could rein it in from 30 minutes and longer to 10. So to render one of these 30-day reports, we have to do these top-end calculations over something on the order of 4 billion flow record documents. In some cases, we would see that these reports covered flows involving over 120,000 unique hosts and 6,000 unique applications. And remember, this is at the end of 2019, and these numbers are only on the increase today. For example, we might ask for the top 5 conversations among these 4 billion documents, and that is a ton of data to comb through just in time. Now, there are a number of different approaches to address this kind of challenge, including pulling all that data into memory and using something like Druid to do this scraping. But we ended up making a different choice. We chose to build a streaming analytics pipeline and pre-compute some of these statistics in line as it goes through the pipeline, resulting in a big speed up when we're presented with these kinds of very daunting queries. That was the genesis of what we're currently calling Nephron, which you saw boiled down to a single tiny little box in that earlier architectural block diagram. Nephron's main purpose is to make these dashboards quicker to load. Now, as a happy side effect, bringing Nephron into the picture dramatically reduced the storage burden on the Elasticsearch cluster. It also significantly reduced the amount of compute required to ingest the flow data. Of course, there's no free lunch, so these improvements do come at the price of adding a whole new component to the solution, and quite a complex component at that. Beyond the added complexity, streaming analytics introduces some of its own unique challenges at runtime. If you've dealt with flows at all, you're already aware probably that things get weird if you don't NTP every device that's involved in a flow solution. Time travel happens, right? Even when you do get this right, though, when you're working in the realm of streaming processing, you can still have time lag introduced because it's grouping every element by a time window. And the size of your network is kind of variable, right? There's different amounts of glass between point A and point B and point C and point N, but the speed of light is more or less fixed through that glass. So sometimes you get late arriving data. Sometimes you get apparently early arriving data. If you're lucky, most of your data arrives apparently on time. Currently in Nephron, we use the Apache Beam streaming framework, which does provide some nice help with these problems, but it's still extremely difficult to engineer around those challenges. At this point, I'm kind of at the limit of my competence talking about these advanced streaming analytics concepts, so let's move it along, shall we? Talking about the future is nice because nobody knows what it will look like. We've accomplished quite a lot in OpenNMS with respect to flows. We're not content, though, and we're continuing to push these capabilities forward. The single biggest thing we want to achieve in the near future is to reduce the complexity of the solution. It is kind of unwieldy the way it exists today. Finding a way to eliminate the need for the Apache Flink cluster as a prerequisite for running Nephron would be a huge win. I have no idea what form that would take, but we have top people thinking about it. Another thing that would be awfully nice is to make it possible to store flow record documents in Cortex without the need for Elasticsearch. The reason we still need Elasticsearch today is that flow data has an incredibly high cardinality. You have to multiply together the number of possible values for every dimension that you care about tracking. For instance, every combination of possible source IP address, every combination of possible destination IP address, times the number of possible source ports, times the number of possible destination ports, times the number of possible layer 3 protocols, which fortunately is a pretty small number, but it's still at least 2, right? And that number gets really, really big, really, really fast. Cortex is just not currently able to cope with that high level of cardinality. So one way that we might help get there is by working upstream in the Cortex project. And in fact, we've recently hired a developer to do exactly that. Finally, while this kind of solution will never be trivial easy to deploy, we can make deployments easily repeatable by creating a Kubernetes operator. That work is happening right now, and it's proceeding nicely. I'm actually attached to the engineering team that's working on that, and I'm happy to say it's coming along swimmingly. I've left time for a small demo in which I'll walk you through how these things look in a real system that I help maintain for our sales team. I'll start in the Minion Appliance portal, which is how I've chosen to set up the minions that are part of this demo stack. Then I'll jump to the OpenNMS web app for a tour of the flow classification interface and a quick look at a node that has some flows on it. I'll wrap up by showing the flow deep dive dashboard in Grafana and how that can be used to isolate the flow responsible for a big spike in interface traffic volume. Just switch my share. All right, so here we are in a pre-release version of the Minion Appliance cloud portal. It will look nicer than this when it launches later this month. It's important to note here that this interface that you're seeing right now is the only non-free part of the demo. It's just the way that I've chosen to deploy the minions for this demo system. It's not actually a necessary part of a solution stack. And behind the curtain, all it's doing is spinning up Docker images, Docker instances using Minion images from our public Docker hub. So everything that actually counts is totally free and open source. You can see here that I've got 3 appliances listed. One is a Raspberry Pi 4. That one has a little padlock on it, which is telling me that that appliance is actually secured via a hardware TPM. This middle one here is a virtual appliance. It's actually unprovisioned and offline at the moment. It's just telling me that there's a seat available on my subscription for it. If I wanted to spin it up and bring it into action, I could do. And then finally, I've got this third one down here that is a virtual appliance. That's an OVA that's deployed in the data center of one of our sibling business units in Phoenix, Arizona. You can see that it's online and activated, and this little blue sash that it's wearing here is telling us that it's a virtual appliance. And those virtual appliances are secured via a VTPM, much like the hardware ones. I'd like to jump into just one neat little feature of this portal. This is, again, totally disconnected from OpenNMS, but even though it is, we can still see some stats on these appliances. So this is the Raspberry Pi 4 appliance. You wouldn't want to use one of these in production, obviously, but you can see that it's chugging along, performing acceptably. It's just part of my home lab setup. I'm going to jump over now to the Instances tab of this interface. This is where we can configure OpenNMS instances. Again, this portal is just tying together the appliances with the OpenNMS instances. This instance is just a Horizon, it's actually Horizon 27. It's a little bit behind the times, but it's a vanilla OpenNMS Horizon, nothing special about it, except that we've put a lot of love into it. And I'd like to show you this connectivity profile feature, which just shows us that we're telling our minions that we spin up how to connect to the web app for the REST API interactions that they need to have with OpenNMS Core. We're telling them the username to use to authenticate, and then the password is configured separately, and that's not shown here. Maybe at least as important, maybe more so, is the Bootstrap servers, which is specific to Kafka. Since we're using Kafka in this solution, we've got sales brokers 01, port 9093, which is the well-known port for Kafka with TLS. I'll jump down here to the feature profile, which I've named Kafka TLS with flows. And this shows us the final bit of magic. All this is doing is on the backside, it's getting translated into a minion configuration via confd inside the Docker instance that's running. So I'm going to show you here what was necessary to get this up and going. Sync is the pattern that we use for receiving flows, as well as traps, syslogs, and streaming telemetry. You can see we're set up for Kafka, and that we've added this extra property here, security.protocol equals SSL, and that's necessary to get Kafka SSL working with the solution so that the minions can talk to it. Finally, down here under telemetry flows, I've switched on the single port listener. I've just told it to listen on port 4729, and that's all. So I'm going to move on and look at the flow classification user interface now. This is in the main Horizon web app. You can see here that we ship with a whole bunch of predefined rules, 6,248 of them to be precise. This is a very long list, of course, and we've provided a convenient search function that is live filtering. So if you're looking for what's on port 666, well, that filters a list pretty far down, and we come down here to it actually being Doom on port 666. So I was wrong. It's not Quake 3, it's Doom. In addition to all these user-defined rules, I'm sorry, these predefined rules, there are user-defined rules that we can create ourselves. So as you can see, we come out of the box with no rules defined, but we can set up our own. I'm going to create a new fake application. I'm going to call it OSMC Jeff G. And the only things I really need to specify here are the protocol. We can specify multiple protocols. And then a source or a destination port. And because today, as you're watching this, is the 9th of November, I'll do 1109. And we'll create that instance. So now we've got this classification rule that recognizes any traffic on TCP or UDP 1109 as belonging to the application I just created, which is called OSMC Jeff G. Now, once you've created one of these, if you've got a whole bunch of protocols that are custom to your environment that you'd like to upload in bulk, you can actually download your current set as a CSV file. You won't be able to see it pop up, so I'm just going to dismiss this download window. But it just downloads it as a CSV file. You can put it into your favorite spreadsheet tool and add whatever other ones you want, and then you can re-upload that CSV, and now your user-defined rules will be much more populated. To show you that, that our classification rule that we just made is actually doing something, I'm going to use the test classification flow right here. So I'm going to say, imagine if we saw a flow on the network that we're on TCP. We have to specify all these things. So I'm just going to put 1.2.3.4 as the exporter. That would be the router or switch that sent the flow packets. And I'm going to use 4.3.2.1 as the source and 9876 as the destination. I'm going to use port 1109 as the port, and we'll hit classify. Oh yeah, this has to be something, right? Classify, and there we go. it may be hard to read, but it did get tagged as OSMC Jeff G. Now, if we change the protocol to ICMP instead and click classify, it would say no mapping found here. So we can tell that that rule that I added does in fact do something. Finally, over here in the settings tab, we've got the ability to create new sets. So in addition to the user-defined rules and the predefined rules, you could actually have multiple sets that are user-defined. So we could add a new set here. We'll call it Jeff rules and blah. Create that. And now you can see we have a new tab up here where I could add my own rules. We can also reorder these things, so we can make it so that my rules go at the very bottom after the predefined rules. Seems to be a bug there. So we'll just delete that and move along. Now I'm going to show you in the OpenNMS Horizon web app. I'm just going to search here. I'm going to type flow into our global search bar, and that'll take me to a shortcut here to show nodes that have flows on them. Here you can see one of the nodes in our Phoenix data center does actually have some flows on it. We have this badge right here that gives you an indication of that. So if you had just tripped over this node in the node list, you'd see this too. And if we move down here to the Snmp interfaces box, we can see there's an ingress flow indicator on many, but not all of the interfaces on this node. This node is just a pfSense node, which uses softflow-D and doesn't support bidirectional flows, and that's why we have only ingress flows on here. Finally, the last thing that I wanted to show off is the real deal. Here we are looking at the flow deep dive dashboard. We're showing flows for the last 6 hours on the same node, this FW cluster node, on the BCE0 interface, which is the outward-facing interface, I think. And we can see here, we're already seeing a spike in the throughput by application and also Snmp interface statistics graphs. So I'm going to use this, this Snmp interface statistics chart as an anchoring point for zooming to a narrower time period. And you're going to see, as soon as this finishes loading, that the throughput by application panel changes its time period to match. And now we can see, okay, the big dominator here is HTTP, right? That's now 76 megabytes per second. And then if we drop down to the very bottom here where this conversation row is, we can see exactly what's going on here. So this may be, again, hard to read in the pop-ups, but we can see that it's an HTTP flow as we thought it would be. And it's between a node called Squid and a node called Action Toad. So I think somebody might have a Super Mario universe thing going on with their node naming scheme. You can also see those same data bits over here on the right-hand side, just in tabular form. So this is a real demo of how you can actually use this flow deep dive dashboard to get very quickly from just seeing a lot of traffic to actually having a notion of what that traffic is. So time for me to wrap up here. In years past, when somebody from OpenNMS, maybe it was me, maybe it was Taurus, maybe it was Ronnie, has stood up on this stage or been a disembodied head upon the screen, I guess. This is the first time that's happening. We didn't have any flow support at all in any of the OpenNMS products. So I feel really good about what we've accomplished until today. We've gone from a total lack of flow support to quite a scalable solution capable of solving real traffic visibility problems at some of the world's largest companies. We still have a lot left to do, and I hope some of you who are watching will take an interest and join in the fun. You can find us on OpenNMS.com. We have a discourse group. We have our own Mattermost if you're into real-time chat. And we'd love for you to jump into any of those channels and get involved if that's something that you're interested in doing. Anyway, I would like to thank all of you for your time and attention. And again, to thank the NETWAYS event team for the excellent job that they've done organizing this event amid so much uncertainty about how things are in the world. And now, if all the tech works correctly, I will take your questions live. See you after the jump.
So let's see if this works. So so let's see if he's inside here. Hopefully. And probably we have to wait. So, here he is.
Hello, check, check.
So, hello Jeff, can you hear me?
Hello.
Hello, can you hear me? Okay.
Hello.
Jeff, can you hear me?
I hear you. Do you hear me?
Yeah, great. Thank you very much for joining us. We're very sad you can't be here in person. I see you have a companion on your shoulders.
Yes, this is our project mascot, Ulf.
Great. Looks awesome. So, yeah, thank you for submitting the talk. It was very interesting. I guess we might have some questions. So if you have any questions, please ask them. My colleague will go over to the microphone. I will repeat them for Jeff then, so he can answer them directly live. So one question from my side is, when you showed the architecture in first place, you said you have Kafka, and then you send them to We can't hear you. Are you muted? Jeff? We can't hear you. I can't hear you. Okay. That's great. I'm not there, so. Okay, Jeff?
Yes.
Okay, I can hear you again. Great. So, one question from my side was, when you showed the architecture, you said Kafka is sending data to Sentinel and then to Kafka. Do you mean a different Kafka instance, or can it be the identical Kafka instance for that purpose?
Oh, it has to be the same cluster.
Sorry?
It's
what?
just a single Kafka cluster.
Okay, great.
But it may use different topics.
Okay, great. The screen just went black, so yeah, I'm not touching that part anymore. So, do we have any more questions? Anything special from you guys? You can't hear him. Jeff, are you still here? Okay, we can't hear you again. So I'm. Okay, we will get it to work, and then I won't touch anything again. So hopefully it will work. No? Let's. Okay, where did the sound come from? I think from there. Wait. Okay. Okay, it's the wrong one. Yeah, technique. It's interesting. So, yeah, that's awesome. It's not working. Just give me a second. Okay. No, we can't hear you. I can't hear you. It's interesting. It's something with the audio is not working. Oh, great. Hier unten. Yeah, we can do it then. Yeah, now we have no internet. That's great. Yeah, that's true. Okay. Let's do it for our Wi-Fi. Well. Okay. So.
Hello.
Hello. So I won't touch anything again right now.
I'm not touching anything either.
I'm standing here, I'm not doing anything right now. So, yeah, sorry for all the difficulties. I think it's very late on your end.
No sweat.
Okay, so do we have any questions for him? That's great. One final question from my side, because you said Cortex is very complicated in general. So, when you talk about complicated, does it mean you have to configure all the streams and event handling manually for each individual part, or why is it that complicated for the configuration?
Well, speaking specifically about Cortex, it's just the fact that Cortex is its own entire stack, right? There's Apache Cassandra under the hood. There's a whole bunch of other components that all also need to be maintained. Somebody needs to be responsible for that care and feeding. So Cortex, Kafka, Elasticsearch, these are all kind of their own whole practice areas that people and companies make a whole career out of supporting for a living. So it helps to have a data team responsible to feed that every morning and take it out for a walk and make sure that it's happy.
Okay, so basically, but you don't, for example, have to, let's say, you want a certain filter for, I want for the last 2 months my data for displaying a dashboard. Do you have to actually modify it inside Cortex to tell, I want to prepare these data streams, or is it something like it's just doing it automatically based on the configuration you have in OpenNMS itself?
Well, you can do it kind of 2 different ways, right? So with respect to our persisting of flow data into Cortex, our Grafana plugins know how to read that data. It comes out of OpenNMS, which is fetching it actually out of Cortex. Our plugins are aware of the formatting of that data.
Okay.
But it's also possible to get more flexibility than our data sources currently permit by using PromQL with the Prometheus or Cortex data source against your Cortex. So you can kind of have the best of both worlds. And that goes not just for your flow data, but also for your regular time series data, like your performance and response time data.
Okay, great. Any questions from anyone here? Okay, so we have not any more questions. I hope, yeah, you stay fine, and hope we see you next year on the next OSMC. Hopefully everything works out then properly. Thank you very much.
I share that hope. Thank you so much. You're a hero for doing the AV.